Good morning and good afternoon, everyone. I'm Yumu. It's my honor to host our first webinar in 2022 and introduce Professor Feng Jiao to you. Professor Feng Jiao was born in China and obtained his bachelor degree in chemistry at Fudan University in 2001, where he worked on catalytic oxidation of phenol using nanostructured iron oxide with Professor He Yonghe. And in the meanwhile, he started his interest in material science and energy research. Then, Professor Feng Jiao studied nanomaterials for energy storage and conversion systematically at the University of St. Andrews in Scotland with Professor Peter Bruce, and Professor Feng Jiao got his PhD degree in chemistry in 2008 before moving to Lawrence Berkeley National Laboratory as a postdoctoral scholar. Professor Feng Jiao spent 2 years in Berkeley collaborating with Dr. Hans Frey to develop solar field technology and joined in the Chemical and Biomolecular Engineering Department at the University of Delaware in 2010. Now, Professor Feng Jiao is the Robert Garcetti Development Professor of Chemical and Biomolecular Engineering and the Director of Center for Catalytic Science and Technology. Professor Feng Jiao's group combines catalysis, material science, and electrochemistry, developing electrochemical devices for solving critical issues in energy storage and sustainable chemical production. Currently, his group is focusing on two major research topics: electrochemical systems for carbon utilization and nanostructured materials for energy applications. Today, Professor Feng Jiao would like to give us a presentation on electrocatalysis for carbon dioxide utilization. Let's focus on Professor Feng Jiao again and enjoy his talk.
Thank you very much, Yu, for the nice introduction. And good morning if you're in California, and good afternoon if you are in East Coast. So today is my great honor to give this seminar at CIC. My presentation talk is, the title is slightly different, carbon dioxide electrolysis for sustainable chemical productions. So first of all, I want to say today is the first day of Tiger Year. So I wish everyone have a happy new year and also have a wonderful 2022. So give you a little bit brief introduction about my research group at the University of Delaware. So my current group mostly focus on, I would say, 4 different areas. I kind of group them together as a design catalyst for different electrochemical reactions. The catalysts range from nanoparticles or different shapes and different morphology and different compositions. And also we develop new tools allow us to probe the chemical reaction at the interface. This is, I see as a critical techniques allow us to understand better what's going on the catalyst surface. And because our group currently mostly funded through Department of Energy, we got involved in a lot of device scale up and system integration type of a project. So we're actually doing a lot of reactor engineering and process engineering. I'm going to talk a little bit about it in today's talk. The last piece we started about 3 years ago is a tech economic analysis effort. What we try to accomplish there is trying to understand the key gaps for this new technology being commercialized. What are the major costs we have to address before they can be cost competitive to the existing technologies. So today I'm going to touch most of these topics because of the limit of amount of time. I won't be able to go very, very deep into each of the topics, but feel free to ask a question if you have any at the end of this presentation. So first I will give a little bit intro on what is CO2 electrolysis technology, what's the basic concepts got involved in developing this type of technology. Then I will tell you a little bit about the latest development from ourselves and also among others. The last piece is I'm going to share with you our latest tech economic analysis and the life cycle assessment of this CO2 electrolysis technology, and trying to answer two critical questions: is this technology economically viable now, and how does this life cycle looks like for CO2 electrolysis compared to the existing routes? So just some electrochemistry 101, I would say, some basic concepts for CO2 electrolyzer. The type of systems we are working on right now is operate at ambient conditions, basically close to ambient pressure, slightly elevated temperature, but we never go beyond, say, 80 degrees C. We are using two electrodes, cathode and anode, and most of my research efforts at the moment focus on the cathode, but actually I will give you an example for the second half of this talk. Actually, anode could also impact on the overall performance of this type of device. And one of the critical component in this system actually is conductive membrane. We are not a membrane group, but over the past, I would say, a little bit over a year, we experienced a lot of challenges associated with the membrane, and we need a lot of efforts actually develop a suitable membrane material for this type of a system. But anyway, the chemical reaction we are most interested is CO2 reduction reaction on cathode, and the competing reaction is hydrogen evolution reaction. And on the anode, we didn't really explore alternative reactions other than just oxygen evolution reactions, because if you want to meet the CO2 reduction at a scale, oxygen evolution reaction is the only option you can have. So what kind of a figure of merit we can judge whether the system is efficient or the catalyst is efficient? So I want to start with thermodynamics. I'm actually teaching undergraduate level thermodynamics last semester. So we have been doing this for a couple of years now. I always trying to remind everyone, thermodynamics actually tell us what's the minimum energy input you have to give to drive this specific chemical reaction. It's defined as delta G equal to minus NFE. Now, and the equivalent potential is the minimum potential you have to put there. Of course, in reality, we actually pay a little bit more to drive a specific reaction, particularly to overcome these activation barriers. We actually use a technical term called overpotential to define the energy penalty we have to give to drive certain reactions. The challenge for CO2 reduction, particularly in aqueous environment, is there are multiple reaction pathways can occur at similar equivalent potential. This table on the right actually summarizes the major product you can make out of this CO2 reduction reaction. Formic carbon monoxide, there are 2 electron reduction product, and methanol, methane, ethanol, ethylene. Particularly ethylene is one of the very popular multi-carbon product, and it's evolved 12 electrons. And if you look at the thermodynamic potentials, they are very similar to each other, plus minus 0.2 volt. And if you're considering over potential, you have to apply to the system. Actually, at the practical, realistic applied potential, you can drive all the reaction at the same time. So selectivity become one major challenge. That's why we need a catalyst, which can selectively promote one reaction pathway and suppress others. The other type of considerations we have to keep in mind is, of course, overpotential is important. That's the energy penalty. At the same time, current density is also important. What is current density? Current density actually is the production rate. You can consider is just a rate function. And in practical applications, you want higher current density to minimize the capital investment. So we really want to have is a system can be operate at minimal overpotential, but extremely high current density. In reality, it's really hard to achieve both in a single system. So there's some trade-off we have to keep in mind. So particularly for CO2 reduction, there's another term I will say we frequently see in the literature is called the Phytic Efficiency. How this is defined is the current density or current flow into your desired product divided by the total current flow through the whole system. Basically is the selectivity of this particular system. So for practical system, we really want to have a high selectivity towards a particular product you are interested. Most of the time, we want a high value product. And this is kind of the challenge why people spend a lot of time in the community trying to looking for efficient catalysts, not only can promote the reaction rate, but at the same time, it can promote the selectivity. So activity and selectivity are the two major challenges in catalyst development for CO2 reduction reaction. Energy efficiency is another technical term, but it's related to the overpotential and the selectivity of the system. This is sort of the combination of these two will define the overall system energetic efficiency. So I will first start with a little bit discussion about the electrochemistry development for this particular system. So over the years, this field have been, I would say, explored pretty throughout, particularly for monometallic catalyst. A very famous paper or book chapter published by Horry actually summarized all the result I actually put together in this particular table is sort of the common monometallic electrocatalyst for CO2 reduction reaction. They are a group of metals that are particularly good for formic acid selective production. And they are a group of metals like gold or silver. They are particularly good for CO production. For multi-carbon product, people are, nowadays are very interested in those multi-carbon products like ethylene or ethanol. Copper is the only one. The only choice can make a carbon-carbon bond. That's a surprising, and there are a lot of efforts trying to beat copper itself, and it turns out it's really difficult. Hydrogen is something you don't want to produce in CO2 electrolyzers, and there are certain metals, they are extremely active for hydrogen evolution, and therefore they are really bad catalysts for CO2 reduction. On the anode side, what oxidation is the reaction we are considering, and based on the environment, either this is a highly alkaline environment, then you can use the non-precious metals like nickel, nickel iron oxide, or cobalt-based catalyst. For neutral acid environment, you have to go precious metal, particularly iridium is the only one actually is stable under strong acid environment. So this is kind of research areas that also need to be addressed if we really want to implement this kind of technology at scale. How we're going to address these precious metals issues, right? They are not abundant on Earth. Can we find non-precious metals, but still reasonable, stable for extensive period of time? As my research group actually back to 8 years ago, we started getting involved in this field. We started to look deeply into developing new nanostructured catalysts for these particular reaction systems. And nowadays, you probably can find dozens of papers on nanostructured catalyst for CO2 reduction now. This is really highly active research area. And there are different strategies either to increase the effective surface area, we call the electrochemical active surface area, by reduce the size of your catalyst, or you can engineering the catalyst itself to enhance the intrinsic activity. These are the two routes, very popular, and people spend a lot of time trying to develop a new catalyst. So today I'm not going to tell you more about how we actually synthesize those catalysts, but I want to emphasize one thing which caught us a lot of attention lately is when you're trying to, yes, sorry. So one of the phenomena we observe lately is when you put a catalyst in a practical electrode or real electrode, commonly it's a gas diffusion electrode to enhance the gas reactant, the CO2 diffuse across the reaction interface, electrode interface. What we found is the microenvironment actually play a very important role in control the activity and the selectivity. For example, the catalyst I just mentioned, this is one of the SEM, the scanning electron microscope image of very bulky copper particles we put on a gas diffusion layer, which is the porous carbon support. And you can find is they just randomly stick on the surface, and it's just not the catalyst itself, but if you zoom in a little bit, you will find is where the reaction occur actually is at the interface when the catalyst surface is properly wetted, and also the gas reactant can rapidly diffuse to the active side. We typically call the triple phase boundary, but actually this triple phase boundary technically is still wrong because it doesn't catch the compressivity, another level of compressivity in a realistic electrode. So if you really zoom in, what's going on here, actually you have is another bender. You have carbon particles, which actually not only conduct electrons, but also provide you some level of hydrophobicity. And then the liquid electrolyte is trying to wet the surface and the conductive charges away from the interface. So the real system actually is very complicated. We actually got involved trying to develop a new tools which allow us to give to have a complete picture of what's going on at the interface. And there are several things. If you didn't play the interface or construct the interface correctly, a common phenomenon observed by many groups is called flooding issues. Basically, the liquid aqueous electrolyte wet the whole interface and also got the diffusion cross partially into this gas diffusion layer, block the CO2 diffusion to the surface of the catalyst. And the end result is you get really poor selectivity and really poor activity. Basically, you just have a lot of hydrogen production in these particular systems. So this is sort of the new frontier areas caught a lot of attention lately. And there are many ways of trying to address these kind of issues, not only control the hydrophobicity, but also you can control the pH values at the interface. Those also are very important. And also how you manage the gas diffusion into the interface and remove all the product, either it's gas product or liquid product. So let me tell you a little bit about how this ties in to the reactor engineering. So I started with the catalyst, and I sort of trying to convince you when you put a catalyst onto a support and trying to use as an electrode, it's totally different, okay? You not only just worry about the intrinsic activity of your catalyst itself, you worry about the environment this catalyst is in. Then when you look into the reactor as a whole, you will find is the polymer membrane play a very important role. Even the anode could play a very important role in control your selectivity. This is not commonly observed in this field. I want to use one particular system we deeply involved in the past couple of years is called a CO electrolyzer. There's a lot of thoughts put on this, why we want to have a tandem process to address the carbonate formation issue in CO2 reduction reaction. I don't want to waste the time on trying to explain it, but a long story short is by doing this tandem process, we're actually trying to address is two issues. One is carbonate formation issue, or you can call it the stability issues. The other one is energetic efficiency issues, okay? So the second example I'm going to tell you is about CO2 electroreduction reaction, which is the second component of this tandem process. So we ask a lot of questions to ourselves. What is the ideal membrane material for this type of system? And also a kind of very important question is, can we generate a concentrated product stream with a high selectivity and at fast reaction rates? Okay, so this concentration actually is very important for your product stream. If you think about in engineering environment, you want to have a practical system. If you have very diluted product stream, it's really difficult to separate out. And the energy cost for separation is extremely high. So you really want is highly concentrated product stream. But how we can engineer the reactor in a way to promote the concentration. And the last point I mentioned is actually we observe the anode reaction actually can help us to address some of the product selectivity issue. This has been ignored, or I never saw any papers actually mention this, but I want to share this, study with you. So some of the new concepts we're trying to bring into this particular work is we first using a very standard catalyst, copper nanoparticle, 50 nanometer as a cathode material, and we use nickel iron oxide as an anode catalyst. We operate the whole system in a highly alkaline environment, 3 mole of KOH. One of the membrane material we pick is from called the Orion TM1. It's an anion exchange membrane in fuel cell. This membrane actually is developed for fuel cells. And they have approved the durability at 80 degrees C for sauna hours. It seems it's worked very well for the fuel cells. So that's why we're actually interested into using this particular membrane material for our systems. And we actually really trying to push the stability test to not just a few hours, but hundreds of hours. So here is some of the preliminary result I want to share with you. Interestingly, what we saw is we can maintain roughly 100 hours stability for this particular system at a cell voltage roughly 2.3 volt. And you can see there's some spikes in the potential profile. The reason for these spikes is at the end of 24 hours, what we did to the system is to replace all the electrolyte with a fresh 3 mole KOH electrolyte. That's why the potential suddenly dropped to roughly 2.2 volt-ish, then steadily increased. And why there's a spike towards the end of this 24 hours period is the product stream become completely dominated by potassium acetate rather than potassium hydroxide, which means there's a dramatic shift in pH of the electrolyte. That pH shift actually caused this cell potential jump. So later on, actually, we have some data I haven't got a chance to plot here, is we actually can completely eliminate those spikes and make the profile extremely stable and flat. For this particular cell configuration, I want to also mention is what we actually achieve is about 60% acetate Phytic efficiency. This is the highest have been ever reported in the literature. Actually, our results haven't been published yet. And the rest of Fhytic efficiency goes mainly into ethylene and hydrogen as the byproduct. And acetate selectivity actually maintained over 50% across the whole 100 hours test. And surprisingly, in the liquid product stream, we only have acetate, a little bit of propionate, but we don't have ethanol, propanol. Those are commonly observed in CO or CO2 reduction reactions. This is a kind of a surprising result. First, we thought maybe there's some difference in terms of the reaction mechanism when we use different catalysts, but we ruled it out because we're just using a very common copper catalyst. And later on, we found is the disappear of alcohols and why it's become acetate and propionate actually is due to this partial oxidation of alcohol at anode. So we actually try to go one step deep into this and try and prove it. So how we prove this? What we did here is we use different anode catalysts. For example, uranium oxide is very typical standard for any systems. And the nickel iron oxide is the one we actually use in this particular study. And what we found is, in terms of cell potential, nickel iron oxide actually is way better than iridium oxide. This is not that surprising because people report nickel iron actually is better than iridium in alkaline environment for OER, oxygen evolution reaction. But if you look more closely, look at this acetate partial current density on the right, what you find is the acetate partial current density for nickel iron catalyst is way higher than iridium oxide. If you take the ratio between alcohol production and acetate production, you will find all the three iridium oxide, nickel oxide, and cobalt oxide, they are more or less similar. Only nickel iron oxide stand out. So then we look into the literature trying to prove our concept. Our suspicion actually is a reasonable suspicion is nickel iron oxide turns out to be a highly effective catalyst for partial oxidation of alcohol to carboxylates. This actually is kind of a proof what's going on in our system is you actually generate alcohol at the cathode, and when the alcohol diffusion to the anode, they got partially oxidized into acetate. That's why you have a higher acetate selectivity, but then almost no alcohol at all. So there's one step you can further improve this, or sort of prove this is in order for alcohol to diffuse to the anode, you need a good membrane which can allow the alcohol diffusion. Of course, you can also pick a membrane selectively block this diffusion. So we have to take one comparison, kind of a control experiment, is pick two different membranes. One have a good alcohol permeability, one have very poor alcohol permeability. What we find is with the one have a good alcohol permeability, we have a high acetate selectivity. The membrane with a poor alcohol permeability, it's just behaving normal as many other groups observed in this particular system. So combined with membrane and the choice of anode, this is a kind of another option you could consider down the road to get a more pure, a much pure product stream, and also at high concentration. I forgot to mention here, the concentration we got in this particular system actually is up to 3 mole, which is way higher than traditional people get at 100 millimole scale. So the last piece, I have about only 5 minutes. I want to share with you a little bit of thought on what about the tech economics? Is it economically viable for this technology to be implemented in to compete with the existing technology? The short answer is it's not ready yet. also it depends on what kind of product you're trying to produce. We first did a survey on what's a state-of-the-art technology having reported in the field for different products. We actually examined 4 major products widely reported: formate, CO, carbon monoxide, ethylene, and ethanol. And what we find is for C1 product, carbon monoxide and formic acid, they are very close. Our projected production costs actually very close to current market price if you can maintain the state-of-the-art performance. This is sort of our conclusion. It's very close. Of course, there's still room for improvement. If you're interested in multi-carbon products, for example, ethylene or ethanol, here is the result. What we found is for multi-carbon product, the production cost is way higher than current market price, which means currently, even you have state-of-the-art performance system, it's just not cost competitive to existing technology. Why is that? It's because for ethylene and ethanol, you consume more electrons than C1 product. It's about 6 times more. For example, if you convert 1 CO2 to 1 carbon monoxide, you need 2 electrons, right? If you convert 2 CO2 to 1 ethylene, you actually need 12 electrons. That's 6 times higher. So the electricity cost actually is dominant in this overall production cost. This green bar actually represent the cost from the electricity. So that's why it gives us a lot of motivation to further improve energetic efficiency, particularly for those multi-carbon products. There's a lot of we need to do in order to be competitive. So this is a sort of a water flow diagram, and it can be found in our recent paper we just published about a half year ago in Nature Sustainability. These have a detailed analysis about where are the areas we can further improve in order to bring the overall cost to a cost close to current market price. For ethylene, we need to go from $2.5 per kilogram to about $0.55 per kilogram. There's a big gap there. Finally, I want to mention is when we're talking about CO2 electrolysis technology, we always say this is a pathway. Potentially, we can address CO2 emission issues. We can reduce, actually can create a potentially sustainable pathway for chemical production. Actually, this is not a complete picture if you really dig into the life cycle analysis. What is life cycle analysis? Basically, is trying to assess the global warming potential for each of the process. That's called the GWP. It's global warming potential. Basically, is assess how much CO2 you're going to emit from each of the proposed systems. So if you propose CO2 electrolysis, the big red and the purple one bar, they represent CO2 emissions simply from the electricity you're going to consume. Okay, because this process is driven by electricity. If your electricity is taken from the grid we have at the United States right now, you're not going to create a new or cleaner technology. That's actually become dirty. The take-home message is you need we need to work together actually with scientists working in other fields to get more green electricity first. You get 80% renewable, then you will reach this break-even point for these electrolysis pathways, and then the purple one actually represent the current state of pathways for ethylene as an example here. This is one of the take-home message I want to give is, yes, CO2 electrolysis looks promising, attract a lot of attention, but please keep in mind, this is a technology driven by electricity, and we need green electricity for this particular technology to fly. and address CO2 emission issues. Finally, I want to thank my group and of course, the funding agencies to fund this work. And also my collaborators over the years, they are all excellent and help me on different things. And thank you for listening, and happy Tiger Year.
Thanks, Professor Jiao Feng. Thanks for your great talk. Students and postdocs could ask questions firstly. May I ask a general question, Professor Feng Jiao?
Yeah, sure, of course.
Except the nanostructure design for the catalyst to create active sites, these days I also find there is a method to change the roughness of the such as electrodes or catalyst to also create active sites on the on these things. So how can you evaluate this idea compared to the nanostructured design?
So they are similar. It depends on what's the what. So keep in mind, I think I need to bring back this slide. Keep in mind how a realistic electrode will look like, and think about even you create your catalyst, how you can convert into a real electrode. Okay, so if you look at the existing technology, people, including ourselves, we are more comfortable to handle nanoparticles type of catalyst because it's easy to spray and make a larger size of electrode and with controllable quality. You can always do some other tricks to create a roughness. And for example, I think back to a couple of years ago, people using this oxidized derived copper catalyst, for example, as one typical approach to create a gray boundaries. But actually what you create is a porous structure of copper with high surface areas. Then if you look at trying to engineer it around a gas diffusion electrode, it's actually possible, but the highly porous electrode particles itself has the challenges how you utilize the internal surface efficiently. So this is a kind of a challenge, at least I see potentially could be a barrier you have to address down the road.
Thank you so much. Jin Huang, please feel free to ask questions.
Hi, Professor. Thank you for the interesting talk. And I have a question in this page 17 in your slides. Yeah, could you please go to that slide?
Okay. Yes.
Yeah, this one, and use a transition metal-based and noble metal-based catalyst to do a comparison, right? And how do you fairly compare them? Because their ECSA or the activity are dramatically different in terms of, like, let's say OER, right, for this anodic oxidation reaction. And
yes, so okay. First of all, the acetate production are mostly coming from the cathode rather than anode. Okay, so on the anode, what you actually address most of the time you actually run is OER, still OER dominated. So the fraction of ethanol you produce on the cathode, which is only counted as 10% of Fe roughly. So if you convert it to mole ratio, this is like 1% of the total product stream. A few percent, probably 2%. And so it has a very minor effect on the current density or overpotential on the anode side. And what we did here is to keep the anode loading as exactly the same. So roughly speaking, the active site is way more than efficient to drive OER. We just want to see how the side effect on this ethanol partial oxidation.
I see. Basically, the anode side has very sufficient OER process,
yes.
right?
Yes.
Another
OER still dominant the reaction on anode. Here.
I see. Thank you. Another comment following this question. So yes. The assumption you said that you have some methanol or alcohol production and it got oxidized. at this anode side. And you used a membrane to prove that point. And I'm wondering whether if you can use like platinum ruthenium base or some like stable arch alcohol oxidation catalyst to prove that. Would that be possible? I mean, if you
it's
simply
possible.
add some
This is excellent question. So there's a thought actually we're trying to do is to pick a catalyst which can do fully oxidized alcohol to CO2. There's a bunch of catalysts that can be considered, but the challenge there is the end product is CO2. It's hard to quantify how much alcohol got produced internally and go through this internal process, eventually end with CO2 again. This is one of the technical challenges kind of stop us from explore those catalysts. But if you can quantify a small amount of CO2 get out of this anode chamber, I think in principle you can study that. Yes.
Yeah, I see.
But I, personally, I would prefer to not produce CO2 in the system, and rather than produce oxalates, I have some value.
I see. Thank you.
Yeah, that's a great thought. Yeah, great idea.
Thank you so much. Anyone has questions could just open your microphone and ask them directly.
Hello, maybe I have just a short question. Feng Jiao, thank you very much for the very nice talk. My question is, how do you calculate the Phytic efficiency for the acetate?
Yeah, I have the same one. Okay. Yeah.
Every time I got that question, so thanks for asking that one. So, okay, the answer is it's hard. It's hard to know accurately how exactly the Phytic efficiency for acetate. But what we did is we run a system at using iridium oxide. We quantify the amount of ethanol. We assume by replacing the anode into nickel iron oxide doesn't change the amount of ethanol produced on the cathode. We use that to back calculate the acetate Phytic efficiency. Of course, there's a lot of assumption there, right? So because with the nickel iron, the cell potential actually slightly shift. So there will be a little bit challenge there or difference there. It's just hard to know exact number. We do our best. That's all I can say.
All right, Feng, I have another question. Yeah, sure. Nice talk. Yeah, Carlos already stole my question, the first question, so I only have one. Because when I read it, I got the exact same question as Carlos did, is how do you get the Phytic efficiency? I do want to ask about your life cycle analysis, because it's important to achieving a mark parity with the commercial value, right? So, I understand electricity is something that as an electrochemist, that we cannot control the cost of electricity. We can control the rest of it, but the big part of electricity we couldn't. So in your perspective, from electrochemical point of view or reactor engineering point of view, what's the biggest thing need to be done in order to have a better prospect to become market competitive?
Okay, so I would say life cycle itself is dominated by how clean is your electricity.
Sure.
So if you think connect that with the cost, I would say go back to this one. The biggest one is still the performance we have. Even I call the stable art, but the stable art is not good enough for these kind of systems to be commercialized. The challenge for multi-carbon product is you need to have extremely efficient system to reduce the energy kind of consumption. So that's actually connect to this one as well, because think about this. This is 6 times of electricity consumption. In order to minimize the cost, you have to build a system extremely efficient, way more efficient than even carbon monoxide. Which is just so difficult.
So it's not just about Phytic efficiency, because it's total energy cost, right?
Yes.
It's also the total energy.
The combination of overpotential and selectivity.
Yeah, and the current density too, right? Because you got to be at certain flux.
Yeah.
So based on your opinion, it's still the design and the energy, Faraday, and the current density, efficiencies and the current density.
Yeah, if you look at this number, 85% selectivity, 50% energetic efficiency.
And that's a high total, yeah.
That's really high. And right now, I don't see any papers actually even close to this at 1 amp per square centimeter. Don't forget that.
That's at a certain current density, right?
Right.
Especially you want it to be durable for 5 years.
Yes, that's another level. To get there, I think in academia environment, it's really hard to improve durability. I think at least my student will complain if I ask them to do 100 hours stability. That's kind of the maximum they want to do.
Yeah,
over there, no.
Yeah. Good to know. Thanks. Yeah.
It's a very interesting talk. I appreciate your effort trying to actually do the economic analysis. So you mentioned a number of times about the energetic efficiency. But I'm curious, what's the best energetic efficiency out there for CO or for ethylene?
Okay, this is by itself, it doesn't mean anything. So this is a kind of a connector to what kind of a current density you actually operate a system. If you operate a system at very low current density, the energetic efficiency can be very high.
Sure.
So, even ourselves, we can achieve 70, no problem at all. But then the current density is just close to nothing, and it's not practical. So if we want a practical current density, then right now, I would say the energetic efficiency for ethylene is at roughly 20–30%.
Okay.
But improve from 20–30% to 50%. This is a big gap.
So actually, maybe if you go back to the previous slides.
Yes.
I'm still a bit confused. So if you mention the ethylene have 20–30% energy efficiency, what about the carbon monoxide?
So carbon monoxide, people claim they can do 2.5 volt, roughly 50%, and the selectivity is close to 100%.
Okay, so if we assume that's the case, why do we have such a large difference in electricity?
Because you consume 6 times more electrons.
Well, every electron you consume actually is stored in the system. So you don't know.
Yeah, but the cost is not. And so this is the tricky part. If you think about traditional petroleum industry, they started with the most negative feedstock, negative reduced feedstock. So the amount of energy you actually put in there for C2 product is way higher than C1 product. But the value didn't add up like that. So like ethylene is about right now somewhere between $500 to $700 per ton, but CO also at a similar price.
Okay, that's interesting.
But the number of electron cost actually is way higher for ethylene. That's the challenge part.
I guess the cost from cost point of view, that's probably correct. But if it's just from pure energy cost point of view, it actually doesn't matter, right?
If you propose that as energy storage medium, maybe, but unfortunately, ethylene is not used as energy storage medium.
Okay, okay.
This is the challenge. That this actually bring up the other kind of a question is if someone want to coupling CO2 reduction to energy storage, not the chemical production, but energy storage. We actually have another case I didn't got a chance to present here is formic acid can be considered as a hydrogen carrier for energy storage. And people can do pretty selective towards the forming right now using either bismuth-based catalyst or tin-based catalyst. But the challenge for that particular system is also the overpotential is pretty high. And formic fuel cell is not a well-established technology yet. So there still need some development there.
Right. I guess
but that's totally from a different angle. It's not for commodity chemical production. It's kind of for energy storage.
Sure, sure. So I'm interested in whether if we consider energy storage, how do you compare CO2 reduction and utilization versus hydrogen production and hydrogen utilization?
Oh, great question. I will say, give me another month. We are going to actually put together a paper trying to compare all the different options for hydrogen carriers for transportation. It's kind of trying to address is, do we consider hydrogen storage route for, say, hydrogen fuel cells? All you can do is using formic acid as a pathway because it's a liquid. It's easy to store and transport, and as a hydrogen carrier. So actually, we did a tech economic analysis with some industry partners. So we actually wrap up that study, going to put together a paper.
Do you have some summary statement on that?
A summary statement, okay. What we look into is hydrogen, of course, is one of the options through water electrolysis. The three alternative options is formic acid, methanol, and ammonia. These are the obvious three, actually, with a cost kind of comparable each other. And the difference there is the scale. At a different scale, different options actually make more sense than others. The cost actually will change with the scale.
Sure.
At a small scale, water electrolysis is not the best option, particularly for transportation, because the storage cost is just way too high.
Okay,
so
looking forward.
Long story short.
Thank you.
Hi, Feng. Thank you very much. It's a great talk. I wanted to follow up on the topic of the durability and stability.
Yep.
And for the nickel iron oxide catalyst, you're driving it at pretty high current density. And this current density has been reported by others. For instance, Curtis Blingwaite, British Columbia, many years ago, published a paper and discovering or reporting the very significant leach of the.
Oh, yes, yes. Oh, you just spot on. So tell you the story here. Yeah, sorry, I didn't got a chance to get into it. When you see the spike, actually at this point, because the pH is close to neutral, it's a pH about 9 to 10. Actually, we lost most of the iron from this system. The catalyst we did is trying to start with the nickel form. We actually deposit the iron onto it, but at a near neutral pH, most of iron actually left the system. So we end with how we get a more flat performance is we limited the concentration of the acetate product stream not to 3 mole, but to 2.5 mole. So the pH is not dropped that significantly, so we can maintain most of iron still on the catalyst side. This is one of the challenges we are facing now. And I heard I talked to some of other people. They told me they have some other ways to stabilize iron into this structure, but we haven't got a chance to look into that yet.
How they can stabilize this, and this is a very important challenge.
Yes. I'm curious. But they haven't got the. They said that they told me, they promised they will send me some sample, but that's before Christmas. I haven't received anything yet, so hopefully I can solve that issue. But stability for the anode is one of the challenges, particularly if the pH have a big drop.
Thank you.
Anyone have questions?
Yeah, I have a question. Hi, Professor Jiao Feng.
Sure.
I have a testing question. So if the pH of the electrolyte change, how to maintain the testing potential to be stable in the stability test?
So, okay. This is the voltage profile. So how we operate the system is we keep at a constant current. This is at 200 milliamp per square centimeter. Oh, sorry, jumped. This is kept at 200 milliamp per square centimeter. So we recorded the corresponding potential, cell potential. That's why when pH shift, you have a big shift in cell potential, which is of course not ideal. You don't want to have that big a big spike. You want to make it more flat, right? Ideally, that's a more stable systems. This is actually we achieved just recently. I haven't got a chance to plot the data yet.
Got it. Thank you.
Yeah.
Anyone has questions? Okay, I think time is up. Let's thank Professor Feng Jiao again, and thank everyone for participating in the webinar hosted by our NSF CSC Center. Now, participants, please feel free to leave, and Professor Feng Jiao and the members at CSC, please stay here for our next session.
Thank you.
Thank you.